Okay, hello everyone. The timeline says I'm now ready to start my talk. So, welcome everyone. I'm really happy to talk again at emBO. I'm Benjamin, and I want to talk about how to bypass MCU debug protections with voltage glitching at home the easy way, at least hopefully the easy way. So, why am I talking about this? Well, last year I gave a talk about getting started with embedded reverse engineering, and essentially be focused on deeply embedded devices. Deeply embedded devices, as in light bulbs, things you don't actually expect to run a lot of software, and devices that achieve a lot with only very limited resources. If you think about these drones, they have a small Cortex M3, M4, some even MS0, and they manage to keep this thing in the air by doing real-time calculations and stabilizing it. Fairly impressive for a small embedded device. So another type of devices that is fairly impressive are devices that can run for sometimes years on a single lithium cell, while they have Bluetooth connection, while they have NFC connection, and for example, the Apple AirTag, which you can use to track your friends without them noticing it because it is fairly small. And at the same time, it can connect to any iDevice to update its location. So I really like these embedded devices. And I talked about how you can break things, and I broke that down into 4 steps. The first is know it, actually get to know your device. You dump the firmware of the device, you analyze the firmware, and then, of course, in the end, you try to change it, to make it better, to make it worse, to change it, do whatever you want. Just have a bit of fun with it. So just a quick recap with knowing it, I'm referring to you grab any information you can find, starting with the data sheets, you do your research, you figure out how to get access, you figure out what memories there are, you figure out what CPU architecture is, you grab some light reading for when you want to go to sleep really fast, and that's it. You know your device, you know how to attack it. Then when you dump it, this is usually where the fun starts. So you want to get the firmware out of your device. If it is something with an external memory, like a micro SD card, extremely simple, grab the SD card, stick it in your laptop, and you have the firmware. Some devices have something that is essentially soldered on, but is still somewhat external, like a flash chip. You can usually just clamp a clamp on it and read it with an external reader, and it will work. Some of these devices can, of course, update themselves over the internet, and because people don't really have space for full SSL stacks, these sometimes communicate um, in plain text, so you might be able to snatch the update from the wire. Or maybe it's even easier, the vendor actually puts up the firmware on their website and you can download it. Now, if you want to go really ham, which is not something you usually do as someone at home just wanting to figure something out, you can actually hire companies to extract the firmware for you. But let's be honest, the tool of choice for you at home that just wants to have some fun is probably going to be a debugger. Because with the debugger, you can just, well, often connect to the device, use the debug interface, extract the firmware that way. So you have the firmware in some way. Now you want to analyze it. As analyzing, I'm speaking of taking this binary dump you get and transforming it into something that looks more like this. Usually you don't get it to this point where it's this readable, but you can get quite close. And the tool of choice is usually some disassembler or decompiler like Ghidra, or if you have debug access, maybe even just observing the program during execution and figuring out what it does. So now you've analyzed it and breaking it. This is the fun part. And honestly, you're on your own here. Fix bugs, introduce bugs, port tune to it, do whatever you want. Just have some fun with it. So that was roughly what I talked about last year. Why am I here again? Because the problem is your tool of choice is a debugger. You want to use a debugger to get the firmware. But there's something called debug protection. Many devices feature debug protection nowadays that tries to prevent exactly what you're trying to do, using the debugger to extract firmware. Debug protection actually comes in many different forms, And last year we looked at how it works on the NRF51 development board. And there, the debug protection actually does not completely disable the debug port. Instead, it shuts down the access of the debugger to the ROM itself. This means you can still read RAM, you can read registers, you can even control execution, but you can't read the ROM contents, which is what you actually want. But as I demonstrated, you still have debug controls, so we could trick the microcontroller into executing code that actually leaked the content we were interested in into the registers, and we can then read these registers using the debugger. And that way we could bypass it with a pure software attack. But let's be honest, this is the old stuff. Nobody uses this anymore. We have something new. We have the NRF52 dev kit. The NRF52 is essentially a direct successor of the 51. Again, it is focused on connectivity, wireless connectivity, by having a really low power consumption, and it includes Bluetooth, it includes NFC, and it includes a Cortex M3 processor, all in one single chip. And yes, actually, this dev board, most of it we don't care about. We only care about this little chip on the right, which is the actual Nordic NRF52. The rest of the dev board is your Sega controller and a whole lot of circuitry that, honestly, my test didn't cause anything else than problems to me. So this is what we're actually looking at. And as you can see, I had to actually solder something. And this means I kind of seem to have violated what I wanted to drill into you last year. Easiest thing first. So why the hell am I starting with hardware attacks? Why do I solder things instead of sticking with software? Well, they change things. If you get again the product specification for this product, and you scroll down to where it says debug access port, and you can see, oh damn, it changed. Instead of reading it, let's just test what happens. So we connect to our dev board, we try our usual things, we lock the device, we connect the Sega probe, and well, Jelling Commander complains that the device is locked. We, of course, ignore the error and just say continue, and we hope we can still sting a step, we can reach the registers, but no such luck. Just no connection is possible. So we have no way to influence the state using software attacks. Well, that is why I actually had to switch to hardware attacks for this one. So hardware attacks is something new. It is not software-based. You attack the hardware directly. You bypass any protection in software and just go one layer deeper. And when we're talking about hardware attacks, usually they're also called something like fault attacks, because the overall goal of a fault attack is you want to bring some piece of hardware into a state where it no longer works in its intended way. For all of us C++ and C developers, you essentially want undefined behavior instead of trying to avoid it at any cost. Because while undefined behavior is going to eat your kittens and set your house on fire, it can also allow you sometimes to bypass debug protections, because with undefined behavior, anything is possible. So when we talk about fault attacks, this is a whole area of research, of practical applications, and you can essentially spend multiple years just looking at it. But just to give you some examples of what fault attacks can look like. On the top tier, you have actual chip modifications. That means you actually modify how the chip looks internally by either destroying connections, by adding your own connections. But this is not something you can do at home. Usually, if you have an electron microscope and the needed hardware to modify chips, well, why are you in this talk instead of playing with your cool tools? So not something for the home gamer. But what you can actually get started with at home is decapping. Decapping means you take your chip, which is usually this black plastic enclosure, and you remove the plastic to expose the actual silicon die. Because inside this black plastic is a small chunk of silicon that actually contains the microcontroller and implements all these functions. This Silicon die is then connected usually via really tiny gold wires to the actual pins or balls on the side or the bottom of the chip. And by using either very, very carefully mechanical force, you can remove the plastic, or you can use some kind of acid that only attacks the plastic instead of the silicon or gold wires. And that way you end up with the bare silicon die, and the chip sometimes still works after this. So now you kept it, and now you can actually try to expose it to environments it is not designed to work in. One fun way to do it is expose it to ultraviolet light. Ultraviolet light is a really energy-intensive form of light, and this interacts in nice ways with flash cells. You can read a lot about it in this paper, and essentially the goal of this paper was attacking a debug-protected STM32F1 or 4 device by decapping it and exposing it to ultraviolet light. And they did this because when you study its debug protection, it has 3 states. It has no debug protection, meaning no security, you can access everything. It has medium debug protection, which in this case means you can only access RAM and registers, which is quite similar to what we saw last year on the Nordic NRF51. And the third state is no debugger access at all, so full lockdown. And these 3 states are stored in a single byte in the configuration region. And the 3 states are encoded using this byte, and 1 byte value means no debug protection, 1 byte value means full debug protection, and any other byte value means medium debug protection. So as you can see, if we manage to flip a single bit, and it doesn't matter which bit we flip, and it doesn't matter what the new value is, we will downgrade full debug protection to at least medium debug protection, or if we get extremely lucky, to no debug protection. So what they did is they decapped the chip, and then they identified where the configuration region is on the chip, covered everything else really carefully with a non-transparent tape, and exposed it to UV light. This caused some bit errors in this region, which resulted in the debug interface being accessible again. Then they added another exploit on top of it, which allowed them to use a race condition inside the chip to actually extract the entire firmware. Really cool paper. Read it, and you can even watch the presentation online. Really can recommend it. But what we are going to talk about are voltage glitching attacks. So voltage glitching. This means we want to in some way interfere with the supply voltage to the chip. And of course, it can be 2 directions we can take. The first thing is overvolting. Overvolting means exceeding the normal operational limits of the device, which carries a high risk of damage. But nevertheless, if you keep it short and you don't go overboard, the chip might survive. And because you used it outside of its normal performance envelope, it might actually cause some errors inside you can abuse. The other direction, of course, is undervolting it. You either drop the voltage to 0 by connecting it to ground, or you drop it slightly below what the chip is designed to work on. You have less of a chance to damage internal components because undervoltage is a condition this chip needs to deal with anyway, for example, during power down. However, when you glitch, you usually drop a voltage line really quickly, and this will cause high currents to flow, which can also damage your device. So try to keep a few more of these on hand, and maybe don't try it on a really expensive laptop. So I just started talking about voltage glitching, but this sounds really hard. I just want to break these things. Why do we now talk about something this complicated? Well, it's not that complicated if you break it down into single steps. Essentially, you need some way to access the supply voltage. You need to figure out when to glitch and for how long to glitch. You need to figure out how to control your glitching process, And because, as I will explain later, in my case, it is not an exact science, I want this automated, so I can retry it every time I want to and use essentially brute force to solve something. And for this, I also need some kind of an indicator that tells me, hey, your glitch was successful, or better luck next time. And in the end, you dump it, but well, we know how to do that once we bypass the debug protection. So accessing the correct supply voltage. Well, this is a dev board, and it has a nice header labeled external supply there, but if we attack there, there's a whole lot of dev board in the way until we get to the actual chip. And these components, they all have some decoupling capacitors that we need to discharge to drop it. They have some capacitance internally we need to discharge. There's just so many variables in there. It's going to be hard. It's going to introduce extra noise. So instead, let's focus on our actual target. As you can see, it is nicely separated from everything else, and there are a lot of components that deal directly with this chip. And one thing you should know is silicon vendors usually provide you with some schematics and reference designs for the power supply of their chip. And in general, system integrators do not deviate from this, because if they do, the question becomes, did we screw something up with our design, or is the chip faulty? And of course, the silicon vendor will point at, well, you didn't follow the reference design, good luck figuring it out. And once you look at this, it might seem a bit overwhelming, but you can easily remove candidates that can't possibly be your target, because you're looking for something that connects to an internal voltage line and that uses an external decoupling capacitor to stabilize this voltage. So you can instantly remove anything that has anything else connected besides ground and a capacitor. So we can, of course, drop things like this with a crystal. We can drop this because there's also a crystal. Well, this connects two different lines via two capacitors. Well, doesn't also look good. This does something weird, so let's also drop it. This connects to the voltage line, not interesting. And in the end, we are left with decoupling 1, connecting via a capacitor to ground, and decoupling 4, connecting also via a capacitor to ground. It also connects to VSS, which is a ground connection if you look it up. So between these two, we look up their functions. DEC 4 is a 1.3 volt regulator supply decoupling. Yay, it's a decoupling capacitor of an internal voltage. And DEC 1, same thing, it's a 0.9 volt regulator digital supply decoupling. Which one you choose? Well, you can just try both. In our case, DEC 4 is what we want to target. So then you need to find it on the circuit board. How you do it, well, depends. If you get lucky, it is clearly marked, like it's marked capacitor 5 on both the schematic and on the board. Maybe you need to do some reversing, usually using your meter in continuity mode, because you know that one side of the capacitor will be a dead short to ground because it is connected to ground, and the other side will not be connected to ground because it is connected to the decoupling pin. In our case, the really small capacitor below the bigger one is our target, and the left side is connected to ground. The right side is connected to the decoupling pin 4. And this is also where I soldered on the jumper wire, because this is the voltage I want to measure, and this is the voltage I want to drop. So great. We have the pin, we have soldered it, and now we can continue on to timing. Timing is difficult because this is one of the core things you need to figure out for this glitch attack. And we're going to break it into two parts. When do we start the glitch? And how long should the glitch be? Because of course, you can determine, do you want a really short glitch or do you want a really long glitch? Usually you want a really short glitch because there's something called a brownout detector. The brownout detector will notice any undervoltage condition and reset the chip. Usually this is meant as a countermeasure against the embedded system running while it is running low on battery and potentially misbehaving. In our case, it will get in the way of our attack because we undervolted. So we want to keep the glitch short so the power brownout detector does not trigger. Also, if you glitch it for too long, you might corrupt more than a bit of the state, which can yield to a condition that can just not recover. So let's look at when. To understand when to glitch, we need to understand what happens once we power up the chip, because even these small devices go through some kind of a boot process. And this doesn't mean like on your desktop PC, you have your UEFI that loads your bootloader at grubs, it then chain loads your Linux kernel, which then starts your user space. Far too complicated. In this case, it is just doing some initial setup and then jumping to user code. And the first step this code will do is it is going to enable critical components. It is going to use some circuit logic to bootstrap the clocks that are needed and any peripherals or memory controllers that are required for the next step, which is starting the actual bootstrap execution. And this will be actual ARM code that is executed. This is burned into the silicon die and runs on the ARM Cortex core inside. The reason for this is initializing all these different peripherals is quite complex. And if you have a nice ARM Cortex M0 or M3 sitting next to you, why not use it and do the whole initialization in software instead of hardware? Far easier, far less error prone. So this bootstrap code will read the configuration and then configure the peripherals. And lastly, once everything is nicely set up, once the user code has a nice blank slate to start from, it is going to jump to the user's code and pretend it was never there. So where in this process can we actually try to interfere? We can try to interfere with enabling critical components, but well, if we screw something up there, the chip is just not going to boot, and well, why do we want to mess with internal clocks? If it's wrong, everything will break. So let's skip this. Starting the bootstrap execution. Again, why would we mess with it? It doesn't do anything evil like disabling the debug interface. So what about reading configuration? Reading configuration sounds really promising because the state of the debug interface is stored in a configuration region. So hey, let's keep this in mind. The next step would be configuring, as in, depending on the configuration, configure peripherals correctly. In our case, for example, configuring the debug interface and disabling it. Well, also interesting, so again, let's mock this down. And the last step is starting user code, and let's be honest, we don't want to mess with user code. In contrast to the bootstrap code, which we can essentially reason about because it has some fixed goals it needs to achieve, user code can do everything. So let's not touch it. So we are left with these two things, and because they are next to each other, we are just going to treat them as one big step, and we are trying to hit it somewhere in this area. So now we know where to hit it, but we need to get our timing really correctly, really tight. So how can we tell where the chip is in this whole process? We can't look at the bootstrap code because it is burned in. We don't know it. It's a black box. But what we can do is observe anything the chip does externally. For example, how much current it draws, or because it is a bit harder to measure, we would need to put a meter in series with it. Instead, we are just going to look at the voltage on the pins, because if you increase the current draw, it is going to drop the supply voltage a bit. So out comes the oscilloscope, and you will see in yellow the supply voltage, the internal supply voltage I connected via the jumper wire. And you will see in blue the overall supply voltage connected to the development board. So let's turn on the power. And as you can see from its 0, the supply voltage spikes. And then once the internal chip starts charging its components, once it starts powering up, and there's a drop, because I think I'm drawing too much current for this GPIO pin I'm doing this from, but well, it hasn't burned up yet, so it's fine. And as you can see, there's a spike in the current, in the voltage. This is the initial spike because nothing is powered on. And then you can see a slight drop off. From this area, down to this, where it starts to stabilize. And this is essentially different components of the chip coming online and increasing the power draw. And now we continue on, and suddenly there is another drop. And this is a really sharp drop. And let's just say we can interpret this as a memory controller for the flash memory coming online. Because up until the configuration region is being read, everything is executing from the internal bootstrap ROM. But now we need access to configure a memory, which is likely implemented as flash memory. And reading flash memory, you need to power up its memory controller, and reading flash memory also costs additional energy. So let's just say this is the voltage drop we are looking for, because now reading configuration starts. There's also some interesting thing you can see why we actually went to all this trouble of soldering something fairly close to the chip, because this drop is extremely sharp. If you compare to the smoother drop in the overall supply voltage, well, it is hard to see here, and the inverse is also true. If we drop the supply voltage, the drop in the internal supply voltage will be far less pronounced, which will make our attack far harder. So now we know when to glitch. Great. Now on to duration. Well, we now know where our error is, but we don't know how big it is essentially, how big we need to make our attack. And this is hard to figure out because we don't really have anything to go on. We don't know the code, we can't cycle count. So in the end, let's be a bit lazy and just say we're going to brute force it. So we solve it by not solving it and saying, we don't care, we brute force. So by skipping this step, we have timing complete, and we can move on to controlling our glitch in a somewhat automated way. So what I did is I used a clone of the Bluepill board. It's a clone because, well, when I started this project, I couldn't find any originals online with decent delivery times. So it's the same chip, just cheaper and from China. And this Bluepill board runs the AirTag glitcher firmware. This is a firmware that was originally developed to glitch the AirTag devices, which use, by the way, the same NR52 series chip, just in a very small form factor, but still the same chip. But it doesn't really matter because this firmware is fairly generic. All it does is it exposes a Siri interface to your PC, and you can send it commands like turn on the power, turn off the power, how much should it delay after receiving a trigger to start the glitching, and how long should the glitch be, as in how long should it pull down the supply voltage. And this is all you need to do to essentially glitch anything. Then, of course, you need to connect this to the actual development board, because up until now, we only have a small jumper wire dangling off it that you can snap off instantly. So enter the breadboard mess. Please note the professional strain relief using duct tape. This is a mess, but essentially it is just a whole lot of wire management. So this is the incoming cable from the decoupling pin 4. This is the debugger connection. I soldered it because I didn't have the correct adapter on hand to connect an external Zegger. And I also couldn't use the internal because due to all the resets I was doing to the power offs, I somehow corrupted the firmware of the Zegger every time I reset it, which meant I would need to reflash it, which slows down the process, and thousands of reflashes can't be good for it. So I just connected an external one and it works far better. The J-Link is connected via these wires, and it's standard J-Link, nothing to see there. And the only component doing anything else other than cable management is a small transistor. One leg of the transistor is connected to ground. One leg of the transistor is connected to the decoupling capacitor and decoupling pin 4, which also goes to the decoupling capacitor. And the third leg is connected to the GPIO output pin of the Bluepill board. So whenever the Bluepill board pulses pin high, it causes the transistor to conduct, which will short the decoupling pin to ground. And this short will actually discharge the capacitor really quickly and then drop the entire voltage down really fast, really reliable. And once the blue board releases the pin, so it goes back low, the transistor will stop conducting, the voltage will recover, and the chip can continue executing. This is just a way to reliably drop the voltage. So we need to orchestrate all of this because we now have multi-components in play. We need to control the J-Link, we need to control the dev board, and for this I'm using just a few Python scripts that talk with PySerial to the Blueprint board, send it serial commands, and on the other side it talks with the PyLink library to the J-Link to just try to debug the target. So now, great. We have automated control, we can prove this to our Hertz content, but we are still lacking some indicator. With indicator, I mean, did our glitch work or didn't our glitch work? And here, well, fairly simple. Can we attach a debugger? Do we have debug access? So indicator, really simple. Dumping it, well, I just added it to the Python scripts. The reason I added it directly is we can't really permanently glitch the device. So every time it powers down and we power it back up, we need to glitch it again to get access to the debug interface. So once the glitch worked, I want to instantly extract the firmware, save it to a hard disk, and analyze it later. This is why the Python scripts also take care of it. So great, we dumped it. We are done. Well, it has been a process. So just to give you a rough idea what we just went through is we figured out where we connect our wire to both send the voltage and glitch the voltage. We figured out what the timing should be using our oscilloscope to locate the point in time where we should start our glitch. We achieved automated control using a small additional embedded device to get accurate timing and cheap I/O pins. We figured out how to get an indicator that we actually have debug access, so our glitch worked. And lastly, we have a way to dump the firmware and get this nice binary dump that is totally readable. So we are done, right? Well, we haven't counted the demo gods yet. So let's see whether this will work. So what I have here is a setup. Give me a second to set up my camera. And this is essentially the view to my workspace, which has, well, you can actually point at things. And you have your dev board, this mess of a breadboard. We have the Blueprint board. We have your oscilloscope far to the right. I will show you screenshots instead of recording it screen. And you have your J-Link. And now what I'm going to do is power on the device. And as you can see, it starts blinking away because I previously flashed the blinky. So let's erase everything to start from a clean state. And flash our blinky again. Ignore the arrows. And now we want to check, can we debug? And yes, it says, yay, device is unlocked. But that's too easy. Let's lock the device. And now it tells us device is locked. But as you can see, it is still running. So we didn't destroy the firmware in the process. So now I'm just going to say, please start glitching. And this will just run automated through the glitching process. And as you can see here, instead of continuously running through our blinky process, it stops and starts. This is because every time we fail the glitch, it just restarts it from the beginning, cuts power, starts it up again, so it doesn't get much of a chance to run through the sequence. You just let this run in the background, and I just show you quickly how simple the Python scripts that actually control this are. So test debug, it is really simple. You just try to connect to the J-Link, to the debugger, and if it doesn't work, well, it does. The debug interface is locked and we can't access it. And the really interesting script is actually glitching. And as I talked about earlier, we are using a bit of brute forcing. So we have this for loop, which sets the delay. And we just brute force through the values in this range and try to hit the correct target. And then we brute force how long we glitch it. And again, a bit larger than it should be, just to give us some additional chances. And as you can see, writing to the glitcher is really simple. You just turn off the device, you tell it how long the delay is, you tell it how big the duration should be, and in the end, you just tell it, go glitch. And what this does is it waits for the trigger pin to go high, waits as a pre-configured delay amount, and then drops the voltage, waits, and releases the voltage again. The trigger pin is usually used to connect it to the chip side of a voltage regulator. However, in my case, I just bypassed it and connected directly to supply voltage. This introduces a whole lot of noise, but it usually still works. Then, after the glitch, we just call, is it unlocked? We test whether we can connect or we can't connect. And yeah, that's it. If it worked, success. If not, repeat everything. And because it's not an exact science, repeat until it succeeds. Usually this takes less than 5 minutes. So let's check on it. And of course, the demo gods do not like us today. And well, it's not working. But because honestly, I expected this not to work, I have some backups. So this is a screenshot of the oscilloscope that shows a successful glitch attempt. And as previously, you can see the whole boot sequence with a huge spike in the beginning, which then drops and then recovers slowly. You can see our drop, which we target, and then you can see here, where we drop the voltage to 0, and look at how small the spike is, and then it continues on in a flat line. And if you zoom in, you can see there's a small V shape, which is because we have capacitors instead of removing the capacitors to have more influence, but it is actually more stable this way. So we drop it, stay there for really only a really small time point, and then we let it recover again, and the chip continues along. And note that this is the maximum resolution I could get of my scope. So this is really quick. And this is the reason we are using another embedded device to get the timing right. And if the glitch works, it is going to be happy. It is going to tell you, yay, success. And then you can look in the hex dump. And what we are looking for is confirmation that we actually read the firmware. And because every one of us read the ARM architecture reference manual for the V6 architecture, well, actually V7 architecture in this case, we know that the first entry, first 4 bytes should be the stack pointer. This is definitely a RAM address, and this looks like the end of the RAM, so looks good. So next entry is the location of the reset vector, which is the address of the first instruction that is going to be executed. So 00, 2B5 sounds good. It's fairly close to the beginning, and we know this is a small firmware. So let's search for 2B4, because, well, it's always +1 due to sump. And let's just disassemble the first few instructions. If you throw it into an online disassembler, we can see it decodes to the usual things you see in the beginning of the execution. You load some constants from memory, you do some operations on them, you do some branching on them, and continue on. So, yay, glitching worked, even though the demo gods are not in our favor today. Now that I showed you how to attack it, What about defenses? What can you do to protect against this? Well, most silicon vendors are actually going to say that's out of scope, not our problem. And to be fair, they might be right with it. It always depends on your use case. But if you want to defend it, improving the accuracy of your brownout detector can be a good choice, because a brownout detector, if it reacts really quickly, will be able to detect our glitch attempt and reset the chip in a response and return it to a safe state where we know everything is okay. But there's a trade-off. If your brownout detector is really sensitive, it might actually trigger a reset, even though it was a normal operating procedure. So take care to design it properly. You can do something in software as well. You can try to configure critical things like the debug state in a redundant way. For example, you can read it multiple times in different places, you can write it multiple times, but you need to be careful, because if you only write it multiple times, well, to the same location, I'm just going to target the last write, because this is the one actually taking effect. So, well, take care. But what you can, for example, do if you have some kind of hardware support, you can have two configuration registers that need to be equal or need to be set to two distinct values that's still unknown by the hardware. And then I would need to target both writes to these configuration registers, which is far harder than targeting only a single write, because I have no insight in the bootstrap code. I need to guess. And I need to guess, did I hit the first one? Did I hit the second one? Did I hit only the second one? Did I only hit the first one? Did I hit both? Well, in that case, I would win. Didn't I hit anything? It's just really hard to know, and it really increases the difficulty. Or you can do what some people do. You can smother everything with epoxy, and honestly, if you do that, I'm not going to bother. I'm not going to bother with isopropyl, with heat, with knives that I'm going to cut myself with. I'm just going to say, screw it. It's not my job. I'm not getting paid for it. It's not fun. So what do I want you to take home from this talk? Well, one thing I already talked about last year, hardware protection is not always effective. There are ways around it, but it gets continuously harder the stronger you make your hardware protection. And you also really need to consider your attacker model. For example, if your attacker model is merely someone who has some interest, but doesn't have a soldering iron, doesn't have an oscilloscope, doesn't know about hardware attacks, the NR52 is actually secure against that, because you actually need to extend your attacker model to someone able to do voltage glitching, or at least be able to read some blog posts on the internet about it and actually solder to it. If that is your attacker model, then NR52 is not secure against it. There's also a whole lot of trade-off involved, because the stronger you make your attacker and you build against it, the more it is going to cost you. Maybe in performance, maybe in money, but you're definitely paying at some point. And maybe the most important thing is voltage glitching is something you can do at home. You don't need a fancy lab setup. You don't need that much equipment. For some devices, you can even do it without an oscilloscope. For example, if the chip is really well known and some people did a lot of research on it, you might be able to just build on top of it and just increase your brute force window. Because in the end, it doesn't matter if it needs to brute force for a few days if you get your foot in the door, because you only need to do it once to actually grab your software, and then you can do the same trick we did last year. You have the software, you erase the chip, you flash back the software, but this time you do not enable debug protection, and you have a fully unprotected device. And as of last year, have fun, break all the things, write about it, tell your friends, just have fun breaking things. As a side note, if you prefer to read about this topic in text form, there will be a blog post coming about this topic on our blog very soon. So watch it, and it's likely going to turn into a series on this topic because, well, there's a lot of content. And with that, I'm at the end of my talk. If you enjoyed it, great. If you have any questions, you can either post them in chat now, or I'll be here for, well, let's face it, a few more hours. So feel free to catch me anywhere, and I'm happy to answer anything you might want to know. So that's it.